Okay, now let's implement the gradient descent algorithm using Jupyter Notebook. Okay, so the first thing we need to do is we need to import NumPy and Matplotlib. So to run the cell, you need to press Shift plus Enter. Alright. Then the next thing we need to do is we need to generate some temperature data in degrees Celsius and degree Fahrenheit. So we have these two empty lists. The first one is for degree Celsius, the second one is for degree Fahrenheit. So we need to use this loop to append degree Celsius and degree Fahrenheit values. So that's the purpose of this cell. So you can generate 50 data pointers using this loop. Okay. Then the next thing is we need to put this degree Celsius and degree Fahrenheit values in NumPy array using NumPy. So in the case of degree Celsius, let's store it using C. For degree Fahrenheit, using F variable. The data type is very important here. We need to use floating points. So this NumPy float64 indicates that the degree Celsius and degree Fahrenheit values are in floating point numbers. Okay, let's run this cell. Okay, now let's plot degree Celsius and degree Fahrenheit using Matplotlib. Right. So you'll have this straight line. So the slope of this line should be 1.8 and y-intercept should be 32. Okay, let's see how they look like. These are degree Celsius values. It ranges from 0 to 49. So totally we have 50 data points. So this dot indicates that these numbers are floating point numbers. They are not integers. Let's see degree Fahrenheit values. It ranges from 32 to 120. Okay, so we'll have 50 data points. Now next, let's see. Well, we discussed already loss function in gradient descent previously, but we need to focus on this cell. So in this cell we are going to implement the gradient descent algorithm. So the first thing we need to know is the amount of data. How many data points do you have? So this Lancy calculates the number of data points. In this case we have 50. So n stores the number of data points. I created an empty list over here, degree, just to store degree Fahrenheit values. Learning rate, let's use 0.01. Let's initialize the variables to 0 and the gradients to 0. Right. Now let's create a loop. The loop ranges from 0 to 49, so totally 50 iterations. So what does this loop do? It calculates gradients with respect to each variable. Okay, let's look at the first variable, which is w. So it calculates gradients with respect to w using this formula: 1 over n summation of I runs from 1 up to n minus 2xi into yi minus wxi plus b. So where is minus 2xi in this equation? Minus 2xi is minus 2 times degree Celsius, this part, and this part of the equation is this part, right? Degree Fahrenheit minus degree Celsius times w plus b over n. So this is an average value, so that's why you have over n. The summation is just this part. Just add these gradients. You need to add these gradients and take the average and store it as a new value over here. You'll do the same thing for dB. Okay, you'll do the same thing for dB. And then the next thing is you need to update the variables. How do you update the variables? You'll take the only variable, then minus the gradient times learning rate. You need to subtract that one, and then the new value should be the old one minus gradient times learning rate. So you'll do the same thing for B2. The main purpose of this loop is to calculate gradients, to calculate these gradients and update the variables. Okay, that is the main purpose of this loop. Now let's run and see what happens in each iteration. So since the loop ranges from 0 to 49, we'd expect 50 iterations. So it starts from 0 and then you have 49 over here, so totally 50 iterations. So let's see what happens in the first iteration. The first iteration, which is 0, the first iteration dw, we already initialized it to 0. It should be 0. Degree Celsius is 0, so everything is 0 because we are multiplying minus 2 times degree Celsius, so all this part becomes 0. So dw is 0. Okay, dw is 0. How about w? W is also 0 because this one was initially 0, this part is 0, so we have w0 over here. Okay, how about dB? The initial value of dB is 0, degree Celsius is 0, this part is pretty much 0, it is 0, but this part minus 2 times 32, it becomes minus 64, minus 64 divided by 50, so dB should be minus 1.28. Okay, then what about B? B equals the only value of B, which was 0. We initialize it to 0. This part is this one times 0.01. It becomes 0.013 because it is minus minus, it becomes plus. That's why we have this value. Okay, so it will iterate until the loop ends. The last value for this iteration gives us W 0.61, B 4.73. So we're not able to get the right solution. So one loop alone does not implement the gradient descent algorithm. So we need to have 2 loops. Okay, we need to have 2 loops. Now the question is, where do you put the loop? Where do you put the other loop? This is the first loop, we call it inner loop. We also need to have an outer loop. So now the question is, where do you put the outer loop? Should you put it over here? Okay, this is one possible option. Should we put it over here, or should we put it over here? So there are 3 possibilities. So where do you think we need to put this loop, the outer loop? So think about this one. Okay, this one, or this one. All right. Okay. Now let's try to implement the outer loop over here. Let's say for epoch in range 120. Okay, let's change this one to epoch. Okay, epoch. All right, so let's put a tab over here. Okay, so let's see what happens. Let's run this cell now. Shift plus enter. Oh, so we need to put this one back. Okay, So what's happening? So the gradients are keep increasing, W is keep increasing. Okay. So this is not the right way to put the outer loop, because if you put it over there, the gradients are keep increasing, the weights are keep increasing. So that's not the proper position for the outer loop. How about if you put it over here? Let's put a tab. Okay, what happens if you put it over here? Let's run the cell and see the results. So what do we have? In every epoch we are getting the same value. Practically it gives us the same results. So that is not the right position for this outer loop. Okay, let's put it over here. Okay, let's put it back. So in this case, what happens? Let's see. So in this case, what happens? It looks like gradients are decreasing. The value of W is close to 1.8 and B is close to 32, right? So this is the right position. So if you look at the last iteration, pretty much the gradients are 0, right? Gradients are 0. The value of the slope, which is 1.8, and the y-intercept, which is B 32. So you got the right solution here. Okay, so this is the right position for the outer loop. Okay, so when you implement the gradient descent algorithm, you need to understand that in the outer loop the gradients should be reset. In the inner loop the gradients should be calculated and the variable should be updated. The variable should be out of the loop, and that's a very important point. So if you understand this, that means you understand how to implement the gradient descent algorithm. So let's see the first epoch. So the first epoch values are the red ones, the yellow one is the ground truth values. So in the first epoch the predictor values are way off from the ground truth values. Okay, so that's what we can see from this graph. So practically we need to use a function to implement the gradient descent algorithm, because functions are really useful. We can reuse codes. In the case of loops you have to go there and then change the variables, but if you implemented them using a function, you simply change the parameters, right? You just simply change the parameters, so you can reuse codes, your code. Okay, so I just generated additional I created some lists to plot graphs. Otherwise these are the two loops that we saw in the previous cell. So inside the outer loop we have the gradients. The gradients should be reset to 0 in every epoch. The inner loop calculates the gradients and updates the variables, right? So that's what it does. So this is implemented using a function, because functions are very useful to reuse codes. Okay, so that's the purpose. When you implement the function, you need to pass the parameters. The parameters in this case is degree Celsius, degree Fahrenheit. These are the W and B values. this is the learning rate, and these are the number of epochs, right? So we need to pass these parameters when you call the function. So if you do that, you will get similar results that we saw in the previous cell. Okay, so as the number of epoch increases, when the gradient is close to 0, right, dw and db close to 0, the slope of the line becomes 1.8 and the y-intercept of the line is 32. So it gets the solution for this problem. It finds the slope and the y-intercept of the line. Okay, so in the first epoch, this is the first epoch, from 50 to 100, this is the second epoch, 100 to 150, the third epoch, fourth one is 150 to 200, the fifth epoch is 200 to 250, and this one is the last epoch for predicted values. Okay, let's plot and see how they look like. Okay, so you'll see this one. So the yellow one is the first epoch, the green one second epoch. Okay, this magenta is the third epoch, and the blue one is the fifth one, and the red one is the last epoch. So what do we observe from here? We observe that as number of epoch increases, predicted values are closer to ground truth values. Okay. Okay, let's plot gradients with respect to loss, mean square error. What does it look like? Okay, if you look at this graph, as the mean square error, which is a loss, as mean square error close to 0, okay, the slope of the line is close to 1.8. Okay, this one makes sense because when the mean square error is 0, ground truth values are close to predicted values. They are very close to each other. In that case, we get the solution. The slope of the line should be 1.8. If you plot y-intercept values with mean square error, which is a loss, okay, loss versus y-intercept values, okay, what happens is, as the mean square error close to 0, okay, the y-intercept is close to 32, which makes sense because the y-intercept of the line is should be 32. So this also makes sense. What happens with the gradients? As the mean square error close to 0, the gradients are also close to 0, right? That's what we observe from here. If you run this cell, you'll see the y-intercept gradients are also close to 0. So if the mean square error close to 0, what happens? The gradients are close to 0 and the y-intercept close to 32, and the slope of the line becomes 1.8, which means it finds the solution for the problem. Okay, that's what we learned from these graphs. Let's see about the effect of learning rate. What happens if you use a bigger learning rate, like so? So in the first case, if you remember, in our case, we use 0.01. What happens if you use 0.1 learning rate? Let's see what happens. Let's pass these parameters. Okay, degree Celsius, degree Fahrenheit. These are weight 1, W1, and B. This is a learning rate. These are the number of iterations. So here we change it. We change the learning rate from 0.01 to 0.1. So what will happen? Let's see. Let's run this here. Oh, yeah, so you'll see a very huge number. So if you have larger learning rates, what would happen is your mean square error or your loss goes to infinity. So the gradient descent will not be able to find the minimum value of your loss. So that is the problem. So the learning rate is a very important hyperparameter. So you need to test. The value generally varies from problem to problem. You need to experiment which learning rate is really good. So the problem is if you use larger value, you will not get the minimum value of your loss function. In this case, for instance, it goes to infinity. So if you put the data, after 14 epochs, the mean square error becomes really very huge. Okay, if you use a very small learning rate, still you will get the minimum value of the loss function, but it will take longer time. So you'll have as the number of epoch increases, still you are closer to the right value of the y-intercept and slope, right? Slope and y-intercept. Here is the slope, here is the y-intercept, but this takes a lot of iterations, right? So if you take very small learning rate, it will take longer time to achieve the same result. If you take bigger learning rates, it will not get the minimum of the function, right? So yeah, so still you are able to find the minimum of the loss function, but it takes longer time to achieve the same result. I hope this will help you to implement the gradient descent algorithm. If you like this kind of videos, please subscribe this channel. Thank you.